Every culture has its creation myth, a story of how life began. For centuries, our dominant myth has been one of solitude. Life, we believed, sparked into existence in a unique, pristine, and isolated pond right here on Earth. It was a beautiful, local miracle. But what if that story is wrong? What if the spark wasn't local at all? What if life was delivered? This is the radical premise of panspermia, and its first, most crucial question is a deceptively simple one. Could life even survive the trip? The journey from one star system to another is the most hellish voyage imaginable. It involves eons of deep freeze in the vacuum of space, brutal bombardment by cosmic radiation, and a fiery plunge through a planet's atmosphere. To suggest life could endure this is to suggest it is virtually indestructible. And the stunning truth is, it might be. Meet the toughest life forms we know, extremophiles, bacteria like Deinococcus radiodurans, which can shrug off a dose of radiation thousands of times what would kill a human. It doesn't merely survive, it literally pieces its shattered DNA back together. Or consider the tardigrade, the water bear. These microscopic animals can be frozen to near absolute zero, boiled, crushed under immense pressure, and even exposed to the vacuum of space itself, and simply reanimate when conditions improve. They enter a state of suspended animation so profound, it's a form of biological time travel. But the proof isn't just in the lab. It's written in the sky. In 2019, the Japanese Hayabusa 2 mission landed on the asteroid Ryugu. What it found was revolutionary. Uracil, one of the 4 key nucleobases that form RNA, the essential messenger molecule for life. And not just uracil. Vitamin B3, a critical organic compound. They weren't just finding rocks. They were finding the raw ingredients of biology, pre-packaged and delivered from the depths of space. The experiment is already running. For billions of years, Mars has been firing rocks into space, blasted off its surface by asteroid impacts. We have found over 300 of these Martian meteorites here on Earth. When we examine them, we find something astonishing. While they show no signs of life itself, they reveal that the conditions within these rocks during their journey could have been surprisingly hospitable. Calculations show that the inner layers would have been shielded from the worst radiation and heat. A microbial stowaway could have, in theory, hibernated safely within its rocky spacecraft for millions of years. NASA's own EXPOSE-R2 experiment attached a package of organic compounds and microbes to the outside of the International Space Station for over a year. When retrieved, some of the organisms, shielded by simulated meteorite material, had indeed survived. The verdict from the harshest laboratory we have access to? Life is far harder than we ever dreamed. So, the answer to our first question is a resounding, paradigm-shifting yes. Life is not a fragile flame, easily snuffed out. It is a tenacious spark, capable of enduring the coldest, most radioactive depths of space. The building blocks are out there, the vessels are out there, and the passengers are tough enough for the journey. This changes everything. It means life may not be the exception. It could be the rule, a cosmic constant. And if that's true, then the spark that began life on Earth may not have been a singular, miraculous event. It may have been a delivery, a seeding. But this raises a new, even more profound question. If life can hitchhike on rocks, was it a random accident? Or could it have been on purpose? If life can survive the journey, then the next question is the mechanics of the delivery. How does a rock, let alone a microbe, actually get from one world to another? The answer is not a gentle voyage on a solar sail. It is a story of cosmic violence on an unimaginable scale. A game of planetary billiards where the balls are worlds and the cue stick is an asteroid impact. Picture this. A massive asteroid, several kilometers across, slams into Mars. The energy released is beyond comprehension. Millions of megatons of force. The impact doesn't just create a crater, it vaporizes rock, blasting a plume of superheated material into the sky. Crucially, deep underground, the shock wave shears off large chunks of the Martian crust, launching them into space at velocities that exceed Mars's escape velocity. In the chaotic aftermath, countless tons of Martian real estate are suddenly ejected into the solar system, becoming new, rogue asteroids in their own right. Locked within these rocks, protected from the initial inferno by their dense mineral shields, could be Martian microbes. In a state of suspended animation, they become unwilling astronauts. Their new home is a barren, airless rock tumbling through the void. Their journey is a random walk through the gravitational maze of the solar system, a trip that could last for millions of years. This is not a theoretical fantasy. We have the evidence right here on Earth. We have identified over 300 meteorites that came from Mars. The most famous of them all, ALH 84001, ignited a firestorm of controversy in 1996 when NASA scientists announced it contained what appeared to be microscopic fossilized bacteria. The debate over those nanofossils rages to this day, but the mere possibility was a seismic event in science. It proved the mechanism is real. Material does get exchanged between planets. But the story gets grander. This isn't just a Mars-to-Earth exchange. This is a solar system-wide game of microbial ping-pong. An impact on Earth could have sent terrestrial rocks, potentially carrying early Earth life, hurtling toward Europa or Enceladus, moons with liquid water oceans under their ice shells. We could be the aliens in someone else's backyard. A rock ejected from Earth billions of years ago could have been the seed that started life on a young, wet Mars, only for a later impact to send Martian life back to a now-ready Earth. The family tree of the solar system could be a tangled, incestuous web. And the scale in time is even more breathtaking. We are living in a relatively quiet period. But go back 4 billion years to the late heavy bombardment, and the inner solar system was a shooting gallery. A cataclysmic rain of asteroids and comets pummeled every planet and moon. This period of extreme violence, which would have been an existential threat to any established life, could also have been the greatest engine for spreading it. The very event that sterilizes one world could be inoculating a dozen others. This theory, Lithopanspermia, rock seeding, paints a stunning new portrait of our cosmic neighborhood. The planets are not isolated islands. They are an archipelago, connected by a slow-moving fairy system of rocks. Life, once it appears on any single world, may have a fighting chance to spread, to try its luck on every habitable platform in the system. It suggests that if we find life on Mars, it might not be a second Genesis. It might be our cousin. And if we find life on the moons of Jupiter and Saturn, they might be our cousins too. The entire solar system could be a single, vast, interconnected biosphere. But this theory relies on random chance, a violent impact, a lucky ejection, a perfect trajectory, a survivable landing. It is the ultimate story of luck, which forces us to ask a question that pushes the boundaries of science and into the realm of philosophy. What if it wasn't random? What if the seeds were not just scattered by chance, but were sown? Lithopanspermia offers a magnificent vision. Life as a cosmic accident, a fortunate contagion spread by the random violence of asteroid impacts. But what if the contagion was deliberate? What if the seeding was not an act of geology, but one of biology? This is the frontier of the Panspermia Hypothesis, an idea so audacious it blurs the line between science and science fiction until the line itself vanishes. This is directed panspermia. The concept was first seriously proposed by none other than Francis Crick, the Nobel laureate who co-discovered the structure of DNA. He looked at the breathtaking complexity of the genetic code, a language of stunning efficiency that appears in life's oldest fossils with no clear evolutionary precursors, and found himself asking a heretical question. What if it's too perfect? What if the origin of life on Earth isn't just unlikely, but literally impossible within the time frame we have? His shocking conclusion? Life must have originated elsewhere and was sent here. The theory is deceptively simple. An advanced civilization, perhaps facing its own imminent doom, seeks to preserve its biological heritage. They wouldn't send starships, they would send genes. They would genetically engineer ultra-resilient microbes, freeze-dry them into a dormant state, pack them into protective capsules, and load them onto a spacecraft. This vessel wouldn't need to land. It would simply cruise through a promising star system and disperse its biological cargo into the primordial oceans of a planet like Earth, a world they had identified as a perfect nursery. It's not an invasion. It's a gardening project on a galactic scale. Is this even remotely feasible? Stunningly, the answer is yes. The technology required is arguably less advanced than what we possess today. We already practice a primitive form of directed panspermia in our own labs. We can encode digital information into synthetic DNA sequences. We can launch probes into space. The idea of packaging microbial spores into a radiation-shielded payload and aiming it at another star system is not a violation of known physics. It is an engineering problem, not a fantasy. But this leads us to the most haunting question of all. Why? Why would an alien civilization do this? The motives proposed are as varied as they are mind-bending. The biological imperative. A simple, unstoppable drive to spread life, a cosmic pollination. Life's purpose is to create more life, anywhere and everywhere it can. The Legacy Act. A dying civilization's final act is not a monument, but a message in a bottle. Their monument is us. We are their living, breathing memorial, even if we never know it. The scientific experiment. Earth is a petri dish. We are the culture. They are the scientists observing from a distance, testing the parameters of evolution. The religious act, a form of divine creation where the gods are not supernatural beings, but a technologically advanced species fulfilling a ritual of genesis. Directed panspermia forces us to confront the ultimate identity crisis. If true, it means our entire evolutionary history, the rise of dinosaurs, the ascent of primates, the development of human consciousness, was not a solitary struggle. It was the flowering of a seed planted by intelligence from another world. We are not just alone, or not alone. We may literally be the product of another intelligence. Our creators may not be gods, but scientists. And Earth is not our home planet. It is our habitat. There is, of course, a profound and unsettling silence. No note, no instructions, no welcome to Earth package. But perhaps that's the point. A true gardener doesn't interfere. They simply plants the seed and lets the sun and soil do the rest. Our curiosity, our science, our drive to look up at the stars and ask, are we alone? That may not be a human impulse at all. It may be the dormant programming in our DNA finally activating. It may be our Creator's only message. Grow. Learn. And when you are ready, come find us. This theory may be the hardest to prove, but it is perhaps the most powerful in what it reveals about our own ambitions. Because as we discuss seeding life on Mars to terraform it, as we plan to send probes to other star systems, we are no longer just talking about the past. We are beginning to draft the rules for our own future as the sowers, and not just the sown, And if our origin was written in the stars, perhaps the final proof isn't buried in a rock, but written in every cell of our bodies. So, if we really did come from somewhere else, where's the proof? You might expect to find it in a rock or a fossil, but the best evidence might be hiding somewhere much more personal, inside you. In your DNA, the instruction manual that makes you, you. What if that manual has a copyright page that says, "Printed elsewhere"? Think of it this way. Every living thing on Earth, every person, every animal, every blade of grass uses the exact same biological language, the same genetic alphabet. It's like every book in every library in the world was written using not only the same letters, but the same words and the same grammar. That's weird, right? If life started randomly in different places, you'd expect different languages, different rules. But there's only one. It's as if everything came from the same source. Here's another strange clue. Many molecules in nature come in two versions, like a left hand and a right hand. They're mirror images. When scientists create these molecules in a lab, they get a perfect mix of both. But life? Life only uses the left-handed version, every time. No one knows why. It's one of biology's biggest mysteries. For some, this isn't a mistake. It's a signature, a preference. Like everyone on Earth agreeing to only use Phillips head screws and never flathead. It feels intentional. Then there's what scientists used to call junk DNA, long sections of our genetic code that seem to do nothing. But what if it's not junk? What if it's something else? Some researchers wonder if parts of it could be like a message in a bottle, or an ancient barcode, showing where life originally came from. Maybe it's not active anymore, but it's still there, like an old stamp in a passport. But perhaps the simplest argument is about time. Earth is 4.5 billion years old. For the first half-billion, it was a burning ball of lava. Then, almost suddenly, in geological terms, life shows up. It's a very short window for something as complex as life to just pop into existence. Maybe life didn't start here. Maybe it had a head start somewhere else, on an older, calmer planet, and then caught a ride here on a meteorite. We didn't invent life. We inherited it. We're still searching for the final proof. If we someday find life on Mars or on a moon like Europa, the first thing we'll do is read its genetic code. If it uses the same system we do, it might be our long-lost relative. If it uses something totally different, that means life started more than once. And that makes our shared genetic code here on Earth even more mysterious. So take a second and think. The same code that's in your cells is in a whale, in a tree, in a tiny bacterium. We are all connected. And maybe, just maybe, that connection doesn't end on Earth. Maybe it leads all the way out to the stars. And if we are all family, isn't it time we went looking for the rest of our relatives? If life really did travel across space, hitching rides on asteroids and comets, then we might not need to look to distant stars to find our relatives. They might be living right next door, in our own solar system. And two of the most promising places to look aren't even planets. They're icy moons, orbiting giant gas planets, hiding incredible secrets beneath their frozen surfaces. First, meet Enceladus, a small, shiny moon of Saturn covered in a thick layer of ice. For years, we thought it was just another frozen rock. But then, the Cassini spacecraft saw something unbelievable. Giant geysers shooting out from the moon's south pole. These aren't shooting out dust or gas. They're shooting out water. Enceladus has a huge ocean of liquid water hidden under its icy shell, and it's spraying that water right out into space. It's like a cosmic water fountain, offering us a free sample. And what a sample it is! When scientists examined those plumes, they found everything life as we know it could possibly need: water, organic molecules, and even energy sources, like little chemical batteries that microbes on Earth love to eat. Enceladus isn't just a frozen ball, it's a potential oasis, a place where life could have been delivered long ago and might still be thriving today. Then there's Europa, a moon of Jupiter. It's bigger than Enceladus, and its icy surface is cracked and broken, like a giant jigsaw puzzle. Under that ice, there's an ocean, one that holds more water than all of Earth's oceans combined. Scientists are almost certain this ocean is warm, salty, and swirling with currents. It might even have hydrothermal vents on its ocean floor, just like those on Earth where life thrives in total darkness, fueled not by sunlight, but by the heat and chemistry of the planet itself. So how do we find out if anything is living there? We don't need to dig through miles of ice. Thanks to those geysers on Enceladus and the cracked surface of Europa, we might just be able to fly a spacecraft through their plumes or scan their surfaces and taste the water. That's exactly what future missions plan to do. NASA's Europa Clipper mission will soon orbit Jupiter, flying again and again past Europa, analyzing those water plumes with incredibly sensitive instruments. It will be able to detect not just water, but complex organic molecules, the kind that almost certainly come from living things. If there are microbes or even something bigger in that ocean, we might soon have the evidence. This isn't just about discovering alien life. This is about discovering our family. If we find life on Enceladus or Europa, the next question will be, is it like us? Does it use the same genetic code? The same left-handed amino acids? If the answer is yes, it could mean we share a common origin. We might be cousins, life that started in one place and spread across the solar system. And if the answer is no? If the life we find is totally different, built on another system entirely, that would be even more amazing. It would mean life started twice in one solar system. And if it can start twice here, it must be everywhere in the universe. We are on the verge of an answer. We are no longer just staring up at the stars and wondering. We are building the tools. We are designing the missions. We are getting ready to knock on the door of these distant, icy worlds. And when we do, we might not find monsters. We might find family. The journey to find where we came from is leading us to the most unexpected places. And what we discover there won't just change science. It will change how we see ourselves and our place in the universe. We stand at the most important crossroads in human history. This isn't about politics or technology. This is about identity. For all of human existence, we've asked one question: are we alone? We now stand on the verge of an answer that will shatter that question forever. Panspermia doesn't just suggest we're not alone, it screams that we never were, that the very cells in your body, the DNA that defines you, might be part of a cosmic lineage stretching across galaxies and billions of years. That the same biological spark that ignited on some distant world also burned in dinosaurs, in ancient civilizations, and now burns in you. This isn't poetry. This is a scientific possibility that changes everything. If life can travel between worlds, then extinction events aren't endings, they're dispersals. Asteroid impacts that wiped out species become cosmic sewing machines. Planetary cataclysms become biological distribution events. Life doesn't die, it migrates. Look at the night sky tonight. Those aren't just points of light. They're potential relatives. Every star system could contain cousins we've never met. Every icy moon could harbor family we thought we'd lost billions of years ago. The loneliness that has haunted humanity for millennia wasn't reality. It was ignorance. And if we find life elsewhere, if we confirm that we're part of this cosmic family, The shock will make every previous revolution in human thought look trivial. Copernicus moved us from the center of the universe. Darwin connected us to animals. Panspermia would connect us to the stars themselves. This is our moment. Right now, we are the generation that will either confirm or deny our cosmic ancestry. We're building the tools to find our family on Mars, on Europa, on Enceladus. We're developing the technology to read the cosmic signature in our own DNA. We are literally hunting for our roots in the stars. The question is no longer, are we alone? The question now is, what will we do when we discover we're not? Will we reach out? Will we protect our cosmic cousins? Will we become worthy stewards of this incredible inheritance? We are not just Earthlings. We are the universe become conscious of itself. We are star stuff that can look back at the stars and understand where it came from. We are the bridge between the cosmic past and the cosmic future. The universe has been waiting billions of years for us to realize we're part of something much, much bigger than ourselves. The waiting is over. The family reunion begins now. If you want to continue this journey of discovery with me, make sure to subscribe to this channel and hit that thumbs up button. Your support helps bring these cosmic stories to life. Together, let's keep exploring the universe's greatest mysteries.